Swayam Prabha. Digital India. Educated India.
Good evening, everybody. So today we will look into the accelerated TensorFlow. So first, we will look into the data pipeline. So we have mentioned that tf.dataset or tf.data, that particular class will give you the flexibility to maintain your data flow pipeline. Right? And different strategies we will see. Also, so before going into that, of course, we will see how to create the models, the three different ways. So the three different ways I mentioned in the last class, that you will have the sequential way, which is the best way to start for the beginners. It is very flexible, and if you want to have more control over definition of the model, then you go for the functional way, or you can go for the subclassing APIs. So these three ways we will talk about. Then we will talk about the data pipelining, accelerated data pipelining mostly. So how you can actually define the pipeline so that your data bottlenecks, all the data bottlenecks from different point of view, maybe processing, maybe opening the files, reading the files, different pre-processing you might be applying. Also, you might be reading data from, let's say, remote sources, right? Let's say from S3 you are reading the data, or maybe from Hadoop cluster you are reading the data. So all these ETL pipeline, the extraction, the transformation, and the load. So all these three pipelines, how you can maintain very effectively to accelerate the models that will be working. And also we will talk about next the distributed training, which is very interesting, because here you will have many flexibilities. That also we will see. We will defining the different distributed strategies very easy, but you need to understand what is the particular environment you are working in, and that way you will be actually able to efficiently use those APIs or higher level abstractions to define what will be the distributed strategy for your particular model training. So let's go ahead to see these three APIs. That, as I was mentioning, that you have the sequential API, which will have particular one input. So maybe this is an input tensor, or multi-dimensional it may be, and you will have one output, which is again one tensor. And in the functional API, you will have these inputs and outputs, but you have, let's say, you have multiple outputs. You can see from these two layers you have multiple outputs, and then you are concatenating to get one. So this is just one use case. You can have any where in between. You can have multiple inputs, multiple outputs, multiple input, single output, and single output, multiple, single input, multiple output, and so on. And in subclassing, you will have to use keras.model. So this is your superclass, and then you will define your layers, and you can connect them as you have done in Python. So mostly we'll focus on the functional API because this is a bit tricky to work with, but once you just understand it, it's very easy to use it in cases like where you will be doing some transfer learning, maybe, or maybe multi-class or multi-stage classification. Okay, so or maybe working with multiple heads of classification or prediction. So different use cases you can use this functional API, and this is very useful. And most of the cases people use TensorFlow just for functional API. Okay? So quick overview of the sequential definition of the model that you have seen in the last class, that we have defined one sequential model from the keras.model and model.add. Then you have different layers, different defined, and like dense layers. You have flattening, you have convolution 2D. So all these things are there. Here we are using one dense layer, two dense layer, and three dense layers, then we are actually, this is the output dense. So this is the output one, and this is the output of this layer is four. This output layer is four. But remember, here we are not defining any input layer. So only the hidden layers that we are defining, and then we are getting the output, because you have only one output and one input. So you do not need to explicitly define the inputs. And just in the compile, you just can mention the which loss you will be using, optimizer you will be using, and just hit the feed, and it will do the training with this number of epochs and with this backslash. So this is the naive way of defining one model in sequential manner. But of course, this will suffice for your, let's say, most of the training models that you'll be working with. Right? But we want to go forward with some bit advanced technique with this functional API. Now let's see the layers first. Okay, so layer one we are defining now. So here all these layers that we have defined here and add. So model dot add this dense layer, this dense layer, and this dense layer. So all these, whatever we are adding, they are making one stack, or let's say completely one graph. And then, so this is a complete data structure itself. Okay, so you do not need to worry about what you are getting in between, right? So this is a complete set. And when you are defining the models or model layers in the functional API, so in the functional API, you need to have the layers. Okay, so dense layer, convolution 2D layer, so any layer that you might have. Now here you see we are explicitly defining the input. So input layer, we are defining, let's say one input will have this shape and with some data, I don't know. So this is just the representation. We will see one such use case and in the end of this session. But let's define the layers first. So layer one, layer two, and output layer. So these three dense layers we have defined. So now you see that this output, so these are the just the layer definition. Now these layers are essentially functions which are callable. Okay, so we are calling this function with input layer. We are calling this function with layer one. So layer one is essentially the definition or output of this particular layer, right? So from the previous layers. Now we are calling this layer with layer two, which is the previous layer. So now you see that we are defining these layers, but we are calling them with the inputs that we are giving. So for this case, we are giving input layer, which is actually we have defined the input as, and then here we are using layer one, here you are using layer. So this definition or this kind of just simple tweak calling of these functions with these parameters or input layers or output layers, and output layer will essentially be the output of your internal, and then you can do the define the model. Okay, so model equal to model, and you define with this input and output set. Now, as I was pointing you towards the flexibility of using functional API in the cases where you will have multiple inputs and multiple outputs. So here you can define a list of input layers. So if you have different inputs, let's say 2-3 inputs, then you can define list of inputs, and as output, if you have multiple outputs, you can have multiple outputs. So basically one list you can create that multiple outputs you have. So this definition actually helping you to define one model with different inputs and outputs. And since each layer is callable now, you can use this layer in anywhere you can for your target model. Right? You can call with any, let's say I want to call this dense layer with this layer one. That also you can do. So you can connect this output layer to that layer. So however you want, you can do this. So this is the flexibility I was talking about for the functionality. And at last, you have the sequence, you have the subclassing way of defining. So this is the keras.model, which will be the superclass for this, and you will have the initializer. So same way you have defined for the PyTorch, then you connect them, and then you define the model equal to this. You create the instance of the model, right? So simple, elegant, and you have different ways of defining models depending on your target model and the flexibility you want to have, you can use either one to create your model, define it. Okay, so now we will move towards the input pipeline definition. Data pipeline is very, very important, and when we are using tf.data, then a new world of input pipeline opens before you, because all the abstractions, APIs are already defined. You do not need to worry about, and all these will work as your C++ optimized code in the backend. So the performance you'll get is very high. Let's define why we need actually the input pipeline, right? Input pipeline means what? You just stack one after the processes from different, let's say, track or uh, uh, different layers of your input or output. Now here, let's say you want to train one data set, and that data set you want to load into your memory, right? So how you are actually doing? Reading the file, then loading that into memory. So before that reading also you have this open stage, right? You have to open the file. Let's say you are working with CSV or maybe a big JSON record, or maybe whatever it might be, right? So the entire data, let's say you have 1 TB of data, you do not have the size or the memory available to feed the entire memory to read and then process that, right? So data might not feed into memory, so you have to pipeline. The pipeline stages are like however you define the stages. It might be read, open, then load, read, open, process, load. So whatever the stages you can define, so different stages you can define depending on the requirement, and you can pipeline them, right? Now, so because in each stage you will have some output, and you need to store that into it. And data might require also pre-processing, as I was mentioning that in that pipeline you might have some pre-processing inside. So before loading and after reading you might have the pre-processing. So you can pipeline that and efficiently utilize the hardware underlying. You can use the pipeline, and you will see how miraculously it will accelerate the entire process actually, of data loading plus training, because training on your GPU will wait for the data always, and it's quite fast. So you need to feed the data, right? And pipelining the data efficiently will help to accelerate. So let's see how to decouple this loading and pre-processing. So as I was mentioning, that inside your pipeline, you might have data loading and pre-processing, these two stages, and you can decouple them from the distribution of the data. So loading will be happening in the end, and before that you need to pre-process it. But how you can actually use efficient pipelining to decouple them and distribute the data for your model training, that we will see in the next. So these are common stages of pipeline: extract, transform, and load. So extract is essentially reading the data from memory and storage, parts of file format, whatever you want to do. And then, so reading data from memory or storage, that means maybe local disk or maybe remote storage or whatever. Okay? Transform is essentially, let's say you want to normalize your data or vectorize your data, or maybe shuffle your data, batch your data, right? All these are different transformations that you want to apply. Then load to the accelerator. So this is the load part where you will, so you have the memory hierarchy. So you want to load from your RAM to your accelerator in the end. So that is the last stage of the pipeline that we see here. So let's see the naive way to do this, right? So first you have opened your data record or file or whatever you have, and then you read, right? So let's say you have read this chunk of data, okay, depending on the size that you want to read into your memory, and then you feed that to your training model. So then you train it, right? And then again, you read the data, and then again train the data, whichever you have read, then again read, then train. So this is the simple sequential way of doing things. This is so if you are not doing anything to make the pipeline available. So this is not pipeline yet. This is sequential, and so this is how it will happen if you do not apply the efficient pipelining that is available with TFW. So this is the simple way of defining. So if you write the code, let's say this is your training loop, right? So for epoch, for sampling data set, so for each data set, you just do this training. So time.sleep is essentially emulating the training step. Basically, let's say I'm saying that wait for this time to see whether my data is available, right? So this is a simple example to emulate this pipelining process, which is referred to your TensorFlow.org guide data performance. You can go to this link and see the entire code here. But here we are showing you how to use this pipeline. Okay? So now this benchmark. Okay, we want to benchmark with the data set that we have created. Let's say artificial data set that we have created. Now, total number of epochs I want to run for 2 epochs, and it will iterate through the dataset. Again, this dataset is TensorFlow dataset, so it is iterable, and you can iterate through the dataset, and you can feed that into the training model. So basically, here you will have the training a forward pass and backward pass and update, right? So instead, for simplicity, we are keeping it wait. That's it. And at the end, you'll have this performance count. Okay, so just to see how much time it is taking. Now the thing is that here, this is the naive way of implementing a training module where will have the data set. So this is exactly replicating the process that you are seeing here on the figure. But what we want to have pipeline. Now you will see that the CPU is opening the file here and reading the file here and waiting for the training to be finished here, and then it will load again the data, and then again the training will start. Now these white blocks you are seeing here, the CPU and GPU is essentially waiting for the data and training to be completed, right? Now, so read is done by, let's say, CPU, and train is done by your GPU. So reading here, CPU is waiting here, and GPU is waiting here and here. Similarly for this one. Now I want to have overlap. That means when the GPU is training, CPU was not doing anything. I want to pipeline it so that the next set of data will be read and it will wait for the training to be started. So basically, if you see that the training was done here and GPU was waiting for this short time. Earlier it was very, very large. Okay. Now the waiting time for the GPU is shortened. And then again, since the data is loaded here, then GPU can start this training, and again the data can be read by the CPU in this blank time or idle time, right? And then again it will start, GPU will start the training. So I can see that we are prefetching the data. So this is one way of arranging your pipeline so that the data can be prefetched for your CPU by your CPU to be available for the GPU to train simultaneously. And how you can do that? It's very, very simple. Just you call prefetch with this parameter tf.data.autotrain. What is this doing? This is saying how many prefetches it will do while it is idle. So if you want to define one number here, 3, 2, whatever, depending on your environment, if you know your CPU well, if you know your GPU well, and if you know what kind of size of the RAM and size of the data you are using, you can define this number manually. Rather, you can take the advantage of tf.data runtime, which will define this auto tune by automatically analyzing the environment and set this number for you. So that's the best way to do things. So this free paging, you can reduce the idle time for the GPU and accelerate your training. Interleaving, if you have, let's say, different data sets to be read. So let's say here two colored reading is doing, but they are being interleaved. That means one is being done at the same time, and at the next timestamp, another one from the data set, another data set will be read simultaneously. So you can see that interleaving of different data sets you can do also. And this interleaving is essentially useful for the cases where you'll have the remote storage. So I mentioned before starting this interleaving and pipelining things that you need to know your environment. So when you are reading your data from your remote storage, there the bottleneck is IO bottleneck, because reading and writing will have different time from different sources you are reading, right? Now, if you interleave, whatever is available, that will fetch the data, read the data. So that way, in that case, you will have accelerated training, and the idle time for the GPU will be very less. And if you were using simple reading with the IO bottleneck, then I mean it is horrible training. So and you can parallelize this interleave process. So dot interleave will actually help you to interleave from different dataset reading, and number of parallel calls, again, you can define the number here, or you can use tf.data.runtime, and the autobean attribute will actually fetch the number yours by the runtime itself. So you do not need to worry how many parallel calls will be there for this interleave. We can do parallel mapping. Now, mapping is very important transformation that you will do mostly while doing or creating this data pipeline. So earlier we had open, sorry, earlier we had open, read, and trim, but here we now have map. Now we want to pre-process the data before loading this. This is another stage in that data pipeline that we have introduced here. Now, what we will do here, this is the naive way, the sequential mapping, where you just open, read, map sequentially, then train, again, wait for the CPU to get the training is done message from the GPU, then it will again read the next set of data. And blah, blah, blah. But I want this to be happening parallel, the mapping to be happening parallel. While it is waiting for the next data to be read and pre-processed, you see how much time it is waiting. I want to just reduce this waiting time, collapse all these rates, collapse the mapping, do the parallel mapping, and you see the waiting time for the GPU has been reduced to from this to this. You will have accelerated. You will have accelerated mapping again. Okay, sorry. So now how you will do that? You just call dot map. So basically this is for the map transformation you want to apply on your data set. And this is the map function. So map function is the transformation you want to do. Maybe let's say you want to increment your data before loading, or maybe you normalize your data by, let's say, dividing it by 255 as you have done for your images. That pre-processing you want to do it in this function, map function, any pre-processing. But this is the simple way you will do definitely. But number of parallel calls, if you define it with the auto-tune, it will just parallelize your reading, fetching, and mapping or pre-processing. Now remember, one very tiny details that we will add into the next section, okay, when we will cache this. Basically, all the things we are doing here still now, it is just happening how it will how the CPU and GPU, here the CPU is doing the mapping and reading. If you are asking why not GPU is doing the mapping, or maybe for this case also this case, parallel case or sequential case, GPU cannot do the mapping because GPU do not have the general purpose processing unit, right? So CPU has it. So CPU can do the pre-processing. So there is no way GPU can do the pre-processing. So it can do only matrix multiplication or multi operation or graphics operation, ray tracing operations. So apart from that, it cannot do anything. So map you have to do inside the CPU. So CPU will do the mapping. So the map number of parallel calls you have to define. Caching is important because now I want to say that why you are applying transformations every time. You do the transformation, you transform all the data and keep it in the cache or memory or the file, wherever you want, with this cache function. That's it. So what is happening here, you can see that for this set of training, it is not fetching, not doing the read and transformation as opposed to the previous method, right? Because all your transformed data is inside your memory. Okay? So it is transforming all the data, keeping it in the memory, and it is not doing anything. That's it. So for the next epoch, let's say this is the epoch. For the first epoch, yes, you do the transformation and load the data. But since that was the time that CPU is taking to pre-process the data and load into your memory, and in the next epoch, it does not do anything. CPU does not do anything because the data is already present inside your memory. So then the GPU will just train. Okay. But one tiny thing again, apply time-consuming operations before cache, and apply memory-consuming operations after cache. So this is the thumb rule for caching. If you have very much time-consuming operations, you do before cache, because that way in the first epoch you will have bit performance here and there neglected, but once the pre-processing is done, then you'll have much faster training in the next epochs, right? But here if you have this function, this transformation function, which is memory consuming, then you cannot do before cache, because you cannot apply all the data to be stored in the memory by caching, because it is memory consuming transformation. So you do that after caching. So this is the simple thumb rule you need to keep in mind. Okay, now we have scalar and vectorized operations. So now you can see here we are opening the file, reading the file, mapping the file. Now map is doing the transformation, and map is called after each scalar data. Let's say I want to normalize the data. So each data will be called, then map function will be called, and then it will map, then next data will be read, next map will be done. So why do that? You can do only one map with all the batch of data but one time. That's how you will do that. This is the vectorized map. How you will do that? So this is the simple way of doing it, batching, because in the batching you will actually batch and then map, right? And you do the batch before mapping. Okay, so because now we are vectorizing the mapping operation. We are giving the batch of data to the mapper to get transformed. And you can see that all this waiting time for the mapping is been just collapsed, and you get very efficient timing for your CPU as well. Usage will be more, and the training will be faster. Now, all this tier of data that we have talked about, but we have also mentioned that TFDS, which is the TensorFlow dataset, is essential to be used for your training, and it has a lot more predefined dataset that you can use. Like here, we are using, let's say, MNIST dataset that we want to use for loading and splitting train. So you use TensorFlow dataset. So TFDS module you use to load your data and batch it or whatever you want to do in the next subsequent processing. And to get more details, how you can use this TensorFlow dataset, you go to the link provided here from the TensorFlow developers, so you can see through the code complete training module for using the TFDs.